Back in Module 8, we learned about energy and we learned about power. And we learned that power is equal to the amount of work that's done in a specific period of time. Now, work has the same units as energy does, and so work is measured in units of joules, and our SI units for time are seconds, so the unit for power is joules per second, which we also called a watt. Now, electrical power can also have, or we can also talk about power in terms of electricity. And so since I know that voltage is measured in joules per coulomb, and I know that current is measured in coulombs per second, if I multiply those two together, then my coulombs are going to cancel out, and that's going to give me joules per second. And so that's also going to be power when I'm talking about electricity. So the equation for power when we're talking about an electrical circuit is going to be V times I equals P. Okay? Now, since I know that Ohm's law tells me that V equals IR, I can substitute this IR in for this V. So I'm going to take IR, and I'm going to substitute it in for that V, and I'm going to multiply by I to get P, and when I do that, that's going to give me I squared R is equal to P. So now I actually just have two equations that are going to enable me to find power, which is helpful because if I don't know the resistance, I may know the voltage or vice versa. And I've got to know the current no matter what in order to be able to find power, but I do have a couple of different options depending on what else I am familiar with as far as that circuit goes. So knowing those two equations, then we can work example 15.2. And example 15.2 says, in the previous example, we learned that a space heater uses a 120 volt wall socket to run and draws 11 amps of current. How much power does it use? Well, since I know what the voltage is and I know what the current is, then it makes the most sense to use this P equals IV equation in order to calculate that. So the current we knew was 11 amps, and we knew that the voltage was 120 volts. And so therefore all I'm going to have to do is multiply those two numbers together, and that's going to give me 1,300 watts. Two significant figures. Okay? Just a pretty simple plug and chug there. And then the second half of this example, a motor draws 1.19 amps of current and has a resistance of 101 ohms. Assuming that the motor is 100% efficient, what is its power output? So here again, in this particular case, I know the current and I know the resistance, so it makes more sense to use P equals I squared R. Now you could use Ohm's law and you could convert it around and end up finding what the voltage is, but you can do it in one step if you do it this way. So since I know that the current is 1.19 amps, if I take that and I square it and I multiply it by the resistance of 101 ohms, you chug all that math out, and that's going to give you a final answer of 143 watts, three significant figures down here. Okay, so again, these problems aren't at all difficult. You're just going to be using the two different equations for power in order to calculate it based on the information that you're given in the problem.